And one last thing I want to talk about is the second or the most important theorem for in the basic Lebesgue theory. So we saw the monotone convergence theorem, which is only relevant for non-negative measurable functions. This theorem holds generally, and it's surprisingly strong. So it's called the theorem of dominant convergence. It's essentially the theorem that we'll use. So say you have a sequence of functions which are measurable. They do not need to be integrable, okay? Just measurable. You don't have to worry about integrability. It's quite easy to to make sure your function is measurable. It's slightly harder to show it's integrable. So that's a good thing that the hypothesis doesn't require you to do that. And assume that these functions approach pointwise to this function f, and I don't mind even putting almost everywhere. So I don't have the right. So the pointwise doesn't have to happen at all points, but at all points except for a set of points of measure 0. Okay, so so far really nothing happened. You have the sequence of functions. You assume the very little about just measurability, and you are looking at the function that. So I'm assuming that there is a function. These functions approach to. Here you don't have non-negativity or monotonicity, so it's not a priori true that there is a limit function even pointwise, but assume that there is a pointwise convergence, not only pointwise convergence, nothing like uniform convergence or anything like that. Okay, but now comes the point. So let's say that there is another function g. It should be non-negative function, okay? And it should be integrable. So that function should be integrable, right? But that's the same thing as saying that it's non-negative and it's measurable and the integral is finite, right? And assume that it dominates all the functions, right? So in this sense, so pointwise, almost everywhere, for every n, the absolute value of fn is smaller than g, right? So this is the picture. If you look at g and reflect it to look at minus g, then all the functions sits almost everywhere within this part of the plane. So assuming only that, you know that first of all, f and each of the fn's are integrable, not just measurable. Okay, so that's already something interesting, right? Once you are dominated by an integrable non-negative function, you are integrable if you are measurable. And not only that, as you imagine, you can exchange the limit and the integral, the order of the limit integral, right? So you get this thing. So that's a very strong theorem. We will see where we use it, but essentially you have a sequence of functions. You know what is the target, like the limit function, and you want to prove that you can at all integrate and also switch the order of integration limit. And to do that, you just have to cook up some function that dominates them. So any kind of boundance condition will be suffices for you, and that's a very strong theorem. That theorem and the theorem of monotone convergence are really the reasons we like Lebesgue integrals, because you can do all of these magics without worry too much about am I cheating or not, because you're not.